Hi Math 215 students. In this video we're going to talk about how to solve a linear system, and we'll use matrices to do so. Alright, so you'll remember in the last video we laid out a couple big questions about linear systems. We want to talk about how to solve a linear system, and that's what the topic of this video will be. And we'll also care about describing the complete solution set. In the next video, part C, we'll talk about how many solutions a given linear system might have and how we can determine what that is with just a little bit of work. And then in the rest of chapter 1, we'll look at different perspectives through which we can understand these kinds of problems and their solutions. All right, for outcomes for this video, by the end of this video, or by the time you're done thinking over its ideas and reading anything you need to support it, you want to be able to do the following. You want to define equivalent linear systems, elementary row operations, and all the terms you see there. You'll want to be able to determine whether a given matrix is in echelon form or reduced echelon form, which we'll describe as we go along. And you'll want to know how to perform row operations on a matrix. We'll talk about pivot positions and pivot columns of a matrix, and you'll want to be able to understand what these are and define them. You want to be able to give a parametric description of the solution set of a linear system, and we'll describe what that means as we go through. All right, now to begin our discussion, I want to draw your mind back to your earlier algebra classes. You've seen systems of linear equations, I would bet, in a previous algebra class, and there you learned a few techniques. The three big techniques that most algebra classes deal with are the following: graphic solutions, solutions by substitution, and solutions by elimination. And we'll spend a few minutes just reviewing what these looked like. Hopefully this will be a bit of a review for you. But if you recall, for a linear equation, for a linear system with two variables, what we usually do, what we can do to give a graphic solution would be to graph the two lines. Because if you take a linear equation with two variables, what you have is the equation of a line. And so I've kind of shown three examples here of pairs of linear equations or pairs of lines. And you'll see different possibilities. They may not intersect at all, these two lines. They may intersect in one point, or in this last example, the two lines actually are, the two equations describe the same line. The one line lies right on top of the other line. Now the idea through a graphic solution was that if you want to find a solution to the system, what you should do is look for a point of intersection. And whatever the x and y coordinates are for that point of intersection, they will give you the values of x and y in a solution to the system. Now, sometimes your system may not have any points of intersection, and that corresponds to the system not having any solutions. And sometimes the system has multiple points of intersection, and we would say that there are infinitely many solutions in this particular case. Okay, now in this middle example, you'll see here that the intersection lies at x equals 2, y equals -2. And if you want to, you can check and see that yes, the blue line is the graph of the blue equation, and the red line is the graph of the red equation. And that point of intersection at x equals 2, y equals -2 does satisfy the system of equations, because 2 minus 2 times -2 gives us 6, and 2 times 2 minus -2 also gives us 6. Okay. Now, if you were to take the pictures, like we've said, you can sort of tell from the pictures what these solutions are. I'll just mention here in passing that in the last system, we have infinitely many solutions, which is not to say that any x and any y will make these equations true. The x and the y do sort of have to be carefully chosen. But take a look at this. If we choose y to be anything, if y is available to be any number you want, and if you let x be -2 times whatever y you chose, minus 12, I think you'll find that these values for x and y we'll make the case that x plus 2y is equal to negative 2, and 5 times x plus 10 times y will equal negative 60. All right. Now, when you have a system of three equations, or three variables rather, each of these equations is the equation of a plane in three-dimensional space. And so if you were to sketch a picture of these three equations, it would look like a configuration of three different planes. Now, I won't point out exactly which picture corresponds to this system here, but the idea is the same as we had before. If you want to find a solution graphically, what you need to do is find a single point with an x and a y and a z coordinate that happens to lie on all three planes at the same time. Now, in this first picture, this point right here in the middle lies on the red plane, the blue plane, and the green plane. And so this point, if these three equations had a picture in planes like this, then that point that lies on the intersection of all three of those planes would give you the x and the y and the z coordinates for the solution to this system. Now, it's also possible, though, that one of these other pictures could be the picture of this system. And in these two pictures, you'll see that the blue and the green plane have many points of intersection, but none of those points lies on the red plane. There is no point that lies on the intersection of all three planes. So a system whose picture looks like this would have no solution. Similarly here, even though any two of these planes have many points in common, there is no single point that lies on all three planes at once. And because of that, if the picture that goes with this system looks like this, there would be no solution. Now, it is possible that the planes you get from a system of three equations with three variables may line up perfectly like this. In this picture, the red, the green, and the blue planes all intersect actually anywhere along this line. Every point on this line lies on all three of those planes. And that would be a situation where you have infinitely many different solutions to the system. Now, unfortunately, we won't take the time to go through and tell exactly which of these pictures goes with this particular system. And in general, visualizing becomes tricky even when you only have three variables. But if you have more than three variables, 4 or 5 variables, a picture, to do it justice, would need to be drawn in 4 or 5 dimensions. And that's not something that we can easily do, and our brains can't easily visualize such a system. And that's the real shortcoming when it comes to solving things graphically. It really is only useful when you're dealing with 2 or maybe 3 variables at a time. If you have more than that, then your pictures would need to involve more dimensions, and it's just not something we can easily visualize. Now, in your earlier algebra class, you probably moved on to a different technique of solution, and that is the solution by substitution. And this one is pretty easy to describe, and it's many students' favorite solution technique. So what you'll do in solving a system by substitution is you'll pick one of the equations, and say we take the first equation, and we're going to solve it for one of the variables. So if I were to move the 3y over to the other side, I would get that x is equal to 3y plus 5. Now this is great because if I know what y is, then I'll know automatically what x is. Now what I'll do in a substitution solution is I'll take this x and I'll substitute it into the other equations if I see an x. So I might take that second equation and write, in place of minus x, I'll put minus the quantity 3y plus 5 plus y plus 5z equals 2. Now the advantage to doing this is I've eliminated an x by substituting for it, and now this equation actually only has it has 2 variables left in it, rather than the original 3 we were dealing with. So collecting those variables, I might put the minus 3y and the y together. I'll just put the minus sign, distribute that over the plus 5 to create a minus 5, and then finally, to clean things up, I'll solve for y in this equation so that just like with the x, I get an equation describing what y is. So if I were to add the 5 over, that would make a 7. If I were to subtract 5z and then divide the whole thing by negative 2, I'll end up with y is equal to 5/2 z minus 7/2. Now, with this equation, I'll take a look here at the last equation. I don't have any x's actually, so this system is not as hard as it could be. I do have a y. If I were to substitute 5/2 z minus 7/2 in for y in that last equation and fill out the rest of the equation, I'll put the plus z and the 0 that I'm supposed to. I only have one equation with one variable, and that's perfect. I can add 5/2 z and z to create 7/2 z. 7/2 z would equal 7/2 if I move the 7/2 over to the other side. And solving for that would give me that z has to equal 1. And knowing what z is, I can now go back to the previous equation. I knew that y was equal to 5/2 times z minus 7/2, so plugging 1 in for z gives me that value. I end up with a total of -1 for y. And then now knowing that y is equal to -1, I can go back to the first equation, put -1 in for y, and that will tell me that x is equal to 3 times -1 plus 5, or 2. Now note that if the first equation had also had a term of z in it, I could go ahead and plug z equals 1 in for the term of z, but because we didn't see a z, all we have to do is plug in the value of y, and we find out what x is equal to. Okay, at this point we have a value for x, and a value for y, and a value for z, and if you were to check x equals 2, y equals -1, z equals 1, whether that is a solution or not, plugging those values into our system of equations will show you that every equation does equal the right-hand side as it is supposed to. Right, so this is the technique of solving by substitution. We take our equations one at a time, we solve for a variable, and we substitute values of the variables we've already solved into later equations until we end up just with a single variable, and then we can solve that using our techniques from algebra that you're well familiar with. And then after that we substitute backwards. We evaluate our previously solved equations to find out what the earlier variables are equal to. Now, as you go along, like I said, this is many people's favorite technique for solving a system of equations based on your earlier algebra classes. But to stir up a little trouble, let me just remind you that in order to do this, we had to do a fair amount of algebraic manipulation. In particular, we had to move variables from one side of the equation to the other. We had to solve for x in the first one, we had to move the z to solve for y in the next equation, and that's something that always happens when you're doing substitution. I'll also mention that because we have to solve for y, that means I have to divide through by a number, and so this introduces fractions very early on, and can't really avoid them often. And so both of those operations, changing the sign as you move a variable over the equal sign, rounding off if you deal with decimal approximations to your fractions, or just dealing with fractions in general, that can trip some people up. Now, lucky for us, computers don't make the same mistakes that we as humans make, so computers can handle sign changes, and they can even deal with fractions pretty well. But in practice, what computers do when dealing with fractions is they convert them into decimals, and their decimals are precise only to a certain number of digits. And so computers, for all their benefits, they introduce round-off errors, and these round-off errors can compound. You can get a bigger error in your final solution because of little tiny errors in each step of your arithmetic. So again, substitution is great for 2 or 3 variables, just like graphic solutions were. But substitutions become a little bit less helpful as you get into larger systems with more variables and more equations. Even if you were to introduce computers, there are some things to be careful of. So for that reason, our technique number 3 that we're going to introduce next will be the best technique for solving these systems of large systems of linear equations. And it will translate the most easily to the language of matrices that we will be using throughout the semester. So what is this technique number 3? Well, it's closely related to the third technique you likely learned in an earlier algebra class. And this is the technique of solving by elimination. The idea is that we will combine these equations in our system usually through addition. Sometimes we'll scale the equations, but adding scaled versions of our equations will cause some variables to be eliminated if we do it right. We'll add, and we'll actually see some variables just cancel out. And canceling out is good for the same reason that substitution was good. You are able to reduce the number of variables to a single variable in a single equation and solve it from there. So let's see how this looks for this particular system of linear equations. Now, we've chosen a fairly simple system. If you take a look at that first variable, x, you'll see that we have an x in the first equation and a minus x in the second equation. And if you were to just add these two equations up, x plus minus x gives you 0x, which we will imagine as just having eliminated the variable x. Now, adding the y's from these two equations gives us minus 2y. Adding nothing to our 5z gives us 5z, and then on the right-hand side, the 5 plus the 2 gives us 7. Now note that I've only used these first two equations. I haven't used the third equation at all. So what you're seeing here is just the sum of the first two equations. Okay, now what we'll do though is we'll take the result, negative 2y plus 5z equals 7, and then we'll take the third equation. Both of these equations only involve y's and z's. So what I'm going to do is add them together, but adding y and minus 2y will not cause any variable to disappear. So before I add them, what I'll do is I'll take that y plus z equals 0, and I'll scale that equation by multiplying both sides by 2. So 2 times the quantity on the left gives me 2y plus 2z. 2 times 0 on the right gives us 0. And now, if I were to take the negative 2y plus 5z that I had gotten before, and that equals 7. And if I were to add that to my scaled version of the red equation, I'll get the minus 2y and the 2y canceling each other out, or eliminating the y's. 5z plus 2z is equal to 7z. 7 plus 0 is equal to 7. And I'm left with a very simple to solve equation. 7z equals 7. Dividing through by 7 gives us z equals 1. Now, if we were to go back to the previous equation, we had negative 2y plus 5z equals 7. Knowing now that z is equal to 1, I can substitute 1 in for z. Negative 2y plus 5 times 1 is equal to 7. If I subtract 5 from both sides, I'll get negative 2y is equal to positive 2. And dividing through by negative 2 gives me y equals negative 1. All right. Now, these are probably sounding familiar because this is the same system we dealt with before. But let's finish the problem. Let's go ahead and plug in the value for y into the first equation. We'll get x minus 3 times negative 1 is equal to 5. Or in other words, x plus 3 is equal to 5, so then x must equal 2. So you'll see that a lot of our last steps were similar to this technique of substitution. We did end up using our solved values for z and then later for y to plug in to find the other variables. So this part of the solution was similar to the previous technique. However, one thing we'll point out just in passing is that nowhere did we have to use fractions. So that may be a plus in your mind. Solving something by elimination often can avoid using fractions, and hence it helps us not make as many arithmetic mistakes if we're working by hand, and we avoid round-off errors if we're working by a computer. All right, now one thing you'll notice is that because we were adding these equations together, it made sense to keep the values associated with x and with y lined up, and with z as well. Now, if we wanted to, we could sort of capture these things by thinking just about the coefficients in each equation and the right-hand side. And remember that the augmented matrix is the matrix that records exactly that information, the coefficients on each of the variables and the value on the right-hand side. So let's take a look at matrices and see how they can be used for these solution techniques. Okay, what we'll do is take a close look at what operations we used in our elimination solution, and we will identify what we call elementary row operations to be performed on the augmented matrix. Okay, you'll remember that we started off our solution by adding the first row and the second row together. And so one of our operations that we'll do with matrices is to replace one row by the sum of itself originally and a multiple of another row. So in this example we have here, we added row 1 and row 2. We added equation 1 and equation 2, you'll remember, to get our negative 2y plus 5z equals 7. And we can get that same information by adding to the second row one copy of the first row. So adding 1 plus negative 1 gives us 0. Adding negative 3 plus 1 gives us negative 2. Adding 0 plus 5 gives us 5. And 5 plus 2 gives us 7. Now you'll see that we end up with the same numbers in that equation that we had, negative 2y plus 5z equals 7, but it's written in matrix form. We've recorded the coefficients with a 0, recording the fact that there are no x's, and a 7, recording the right-hand side. Now this is important. We call this a replacement row, replacement operation rather than an addition operation, because we are actually replacing one row of the matrix. That second row is removed from the matrix because we are adding to that second row a multiple of the first row. Okay? Now, if I wanted to, I could have taken the sum of row 1 and row 2 and replaced row 1 with them. I chose to replace row 2 because that also works. I'll only do one of those operations though. I'll replace one of those rows by the sum of that row and a multiple of one of the other rows in the earlier matrix. Okay, that is our first elementary row operation. Our second row operation deals with scaling. So the operation is to multiply all entries in a row by a constant. Now you'll remember that in our solution earlier, in combining the negative 2i plus 5z equals 2 and adding that to the last equation, we wanted to eliminate the y's, and the negative 2y we had earlier wouldn't cancel with 1y, so we needed to scale that equation by multiplying by 2. And in the same way, the coefficients in that last equation being 1, 1, and 0, and then a 0 for that missing x, what we can do is multiply all entries of a row by a constant. Now we're only doing this to one particular row, and the constant that you use has to be multiplied onto each term of that row. But I could take 2 times row 3 and get 2 times 0 is 0, 2 times 1 is equal to 2, 2 times 1 is equal to 2, and 2 times 0 is equal to 0. And you'll notice that I have sort of recorded in shorthand the idea that I'm taking row 3 2 times that to replace row 3. This becomes my new row 3. Okay. All right. Now, a third elementary row operation that we will often perform deals with interchanging two rows. Now, we didn't actually do this explicitly in our solution by elimination, but it will be handy for us occasionally. So one thing we could do is take a look at the second and third rows, and if I wanted to switch them, I could write the third row's coefficients or numbers in the second row spot and the second row's numbers in the third row's spot. And I have interchanged those two rows or swapped those. Now, if you think about what's happening here, each of these rows was supposed to correspond to one of the equations in our earlier system. And if you remember that, it makes sense why switching the rows wouldn't necessarily change much about the system. If I were to swap the location of the second and the third equations, it doesn't change what those equations are requiring. It's just recording the information in a slightly different way. Okay, now this list of elementary row operations that we've dealt with, the replacement operation, where we replace a row with the sum of it and a multiple of another row, the multiply or scaling operation, and the interchanging of two rows, these are three very special operations that we'll need to remember as such. So these are the three elementary row operations. They are the only elementary row operations we will deal with in our course. So remember please what they are, and in particular, remember the restrictions. So in particular, the most restrictive of these steps was this one, where if you wanted to do the replacement operation, you only get to multiply one of the rows, a multiple of the other row, and you have to add that to the original version of the row that you're replacing. So I'm going to take 1 times the third row and add it to the second row. I'm not allowed to scale 2 different rows, and I'm not allowed to replace more than 1 row in a single replacement operation. So this is perhaps the most technical of the steps. It is the most useful, and you may come to agree, but remember this list. Okay, now when we did our solution using the elimination technique, we ended up getting these 3 equations, right? We took the first 2 equations and added them to eliminate the x, and then after taking 2 times the third equation originally and adding that, we ended up with 7z is equal to 7. And this is where we ended up solving. We solved by dividing the last equation by 7 to get z equals 1, and then you'll remember we substituted z equals 1 to find out what y equals, and then we substituted the value for y to figure out what x equals. Now, we're mentioning this because it was at this step that our solution technique kind of shifted. We had sort of a backward substitution phase. Now, you reach that phase, that switch, when you get your equations to look like this. And in matrix form, the augmented matrix looks like this. So we will take a look at this and give a special name to matrices in that form. Now, we'll say exactly what that name is in just a second, but if you'll remember, what we did was back substitution, solving for z, plugging that back in for the second equation, solving for y, and plugging that back in. We could do that here, but we can also use our same elementary row operations as before to continue to solve the matrix, to solve the system in matrix form. So in particular, you know, if this were an equation, we would just divide through by 7 and we'd get z is equal to 1. Well, what I can do is multiply that third equation in this augmented matrix in this form, multiply that third row by 1/7. And if I do multiply by 1/7, each term, remember, gets multiplied by 1/7, and we end up with a row reading 0, 0, 1, 1. Now, if you remember what these coefficients stand for, 1 is the coefficient on z, and 1 is the right-hand side. So this row corresponds to the equation z is equal to 1. We get the same information as before, thinking of it not as dividing by 7, but rather as multiplying, scaling that third row. Now, if we wanted to, we could continue. What I might do is take -5 times the third row and add it to the second row, and replace the second row by that. So we're taking the second row, we're adding a multiple of another row to it, and then putting the result in place of the second. Now, you might not see immediately why we would do this, but take a look at what happens if we do. -5 times the third row is going to give us 0, 0, -5, -5. And when I add that row to the second row, 0 plus 0 gives us 0. -2 plus 0 gives us -2. 5 plus -5 gives us 0. And 7 plus -5 gives us 2. So we end up with this system here. And if we were to scale that second row by -1/2, we can read the result off as 0 times -1/2 is 0. -2 times -1/2 gives us +1. 0 times -1/2 gives us 0. And 2 times -1/2 gives us 2. A -1 rather, sorry. -1. Okay. Now once again, if you think about the equation that this corresponds to, you'll see that we read this off as 1y is equal to -1. And so we get that same information that we had seen before, y is equal to -1, that is revealed to us through our elementary row operations. And then to finish this off, if we wanted to, we could get rid of this -3 here by taking 3 times the second row and then adding the result to the first row. So let's see that happen. 3 times row 2 would look like 0, 3, 0, -3. And if I were to add that to row 1, 1 plus 0 gives us 1. -3 plus 3 gives us 0. So we put a 0 in the second position there. 0 plus 0 gives us 0, and then 5 plus 3 times -1, 5 plus -3 gives us positive 2. And so that first row corresponds to the solution x equals 2. We see that the solution we have, x equals 2, y equals -1, and z equals 1, is exactly the solution we had from our solution by elimination. But we didn't have to divide this into a back substitution phase and a first half. We can just use elementary row operations the whole way through from the beginning to the end. And if we can get to this form here, and if we can then get to this form here, we're able to find the solution to our system. All right, now one quick concept we may be a little bit worried about. In our solution processes, we ended up changing the system of equations we started with. We had this system of equations to begin with, and then almost immediately we started changing it. We replaced that second equation by -2y plus 5z. The third equation eventually became 7z is equal to 7. And then this is a different system than this is. And what's more, if you start solving for z and then y and then x, you end up with what you could consider another system of equations, which is not exactly the same, not identically the same as this system, and certainly not identically the same as the system you started with. And the question is, do we need to be concerned that we're leaving the original system of equations behind and we're changing it, we're replacing it and scaling it and all kinds of things? One important definition to make here is that two systems of linear equations are equivalent if they have exactly the same solution sets. So these systems of equations are not equal, they're not identically the same, but hopefully they're equivalent. Hopefully the solution to this last one, which we see spelled out there, actually is equal to the solution to the first system. And if the solution sets are the same, we'll say that the systems of the linear equations are equivalent. Now, thinking about matrices, two matrices are row equivalent if one of the matrices comes from performing elementary row operations on the other. So we had started with this matrix corresponding to our original system, performing some elementary row operations. We ended up with this matrix that corresponds to this system, but it was all done through elementary row operations, and so we would say that these two matrices are row equivalent. And what's more, as we just saw in the last couple of slides, continuing to perform elementary row operations on the middle matrix produces the last matrix. And so these two matrices are also row equivalent, and what's more, the first matrix and the last matrix are row equivalent as well, because we can get the first one, get the last one rather, by performing several elementary row operations on the first. Okay, now the big important fact, the theorem that we want to state here, is that if you transform a linear system's matrix using any combination of elementary row operations, then the resulting systems, the resulting matrices, they're all equivalent. The systems are equivalent, the matrices are row equivalent, and this is where elementary row operations become important. Remember that list of 3 elementary operations we spelled out before: the replacement operation, the multiplying operation, and the interchange operation. Those are the steps that you are allowed to do and still be able to conclude that the solution set is the same, that the system you end up with here has exactly the same solution set as the original system. So these elementary row operations are safe in that they don't change the solutions. They give you a solution, actually. They make things easier to work with, but they don't change the values that form the solution of the original system. Okay, we're going to end this video here just because it's a good stopping place. In the next video, what we'll do is talk about using these ideas, this terminology, to find a technique for solving any linear system, and we'll do it using an augmented matrix and these elementary row operations. So I will see you in the next video. We'll finish this technique of solution. See you then.